Hello, in this video, let's talk about the DeBroglie wavelength and also the Heisenberg uncertainty principle as we delve into the world of quantum mechanics. And so let's first talk about DeBroglie, who was a French physicist who won the 1929 Nobel Physics Prize. DeBroglie said that electrons and atoms behave like standing waves, and that only certain wavelengths are allowed. So a standing wave, we could say the guitar string being plucked, you could have a half wave going along from one length of the guitar to another. You could have a single wave, complete wave, that then reflects, bounces back, or you could have something that looks like that. And that's for a guitar. If you look at an electron and you think back to Bohr's version of things, you got an electron traveling a wave around a nucleus, and where it starts in an orbit is where it has to wind up as it finishes the orbit, and start back on the same loop. So that's what we mean by a standing wave. DeBroglie said that particles in motion can be treated as waves. And that waves exhibit the properties of particles. And so this wavelength is equal to Planck's constant divided the mass divided by the u, the velocity of the particle that we're looking at. And so let's do this for an electron, and for grins, let's then compare it with the Kia Forte. So we're looking at something, electron that's in the nano world versus something that's in the macro world, the world that we can see at Kia Forte. And so for an electron, Planck's constant, of course, is 6.626 times 10 to the minus 34th joule seconds. Let's write out what joules means. It means kilograms times meter squared over second squared. But Planck's constant is joules times second, so I need to add that times second in there. Divided by the mass of an electron, which is 9.1 times 10 to the minus 31 kilograms, times its velocity, which is 2.2 times 10 to the 6 meters per second. And if we plug that into our handy-dandy calculator, we'll come up with 3.3 times 10 to the minus 10 meters. Well, let me prove to you that it's meters. Let's go through our unit analysis, our dimensional analysis. So kilograms divided by kilograms cancels. I've got second, and looking at the numerator, I've got seconds over second squared. So this second would cancel out the square. And now I've got 1 over second divided by 1 over second if I look in the denominator. And so now those cancel. And I'm left with meters squared divided by meters. Meters squared in the numerator, meters in the denominator. So that square will get canceled out by that meters. And I'm left with units of meters that's uncanceled. So that's what the DeBroglie wavelength for an electron is, which puts us somewhere in the X-ray region of this electromagnetic spectrum, if you want to think about it. If we do this for a Kia Forte and plug this in, H is Planck's constant, the mass now would be 1,280 kilograms. The velocity would now be 33 meters per second. That DeBroglie wavelength calculates to be 1.6 times 10 to the minus 38th meters. Something that's just infinitesimally small. And so we're not going to see such a wave for these macro objects because they're moving so much smaller and they have such much greater mass. And so when you plug those in, that makes for a teeny tiny number, if you want to think of it that way. And so the implications for this is that this has an effect on the atomic world, and this has no effect in the macro world, the world that we see. Let's look at the Heisenberg uncertainty principle that was formulated by Heisenberg, and he's a German physicist, and he won the 1932 Nobel Physics Prize. And he said that it's impossible to simultaneously know the position and momentum of a particle with certainty. That means we can only talk about probabilities. And this drove Einstein nuts. He said that God doesn't play dice with the universe. But this is what Heisenberg came up with, and it certainly leads to our understanding of quantum mechanics when we look at the electron around the nucleus and talk about the probability of finding an electron. So Heisenberg's uncertainty principle. It's possible to simultaneously know the position and the momentum. Let's let position be described by x. Momentum physicists use a symbol of P for. What momentum is mass times velocity. So m times u, where u is velocity. So Heisenberg, the uncertainty in x times the uncertainty in the momentum has to be greater than or equal to Planck's constant divided by 4 pi. So we plug into this kilograms divided by kilograms cancels. Meter squared over meter cancels the square. We'll be left with meters. And then seconds over second squared cancels the second, or the square, and it cancels out one of those seconds. And then we have 1 over seconds divided by 1 over seconds cancels. That leaves us with meters. And that would give us an uncertainty in x of 2.6 times 10 to the minus 9th meters for an electron. If we do this for the Kia Forte, plug those numbers in once again, except using the mass of the Kia and its velocity, what we will see is that delta x has to be greater than or equal to 1.3 times 10 to the minus 37th meters. So what's the practical significance of this? What the significance of this is we look at the size of the Kia Forte. Let's say it's 3 meters long. If you look at 10 to the minus 37th meters as an uncertainty, as opposed to the size of that Kia Forte, it's just infinitesimally small. But if you look at an electron, that uncertainty in position at delta x is 2.6 times 10 to the minus 9th meters. Well, what's the size of an atom? It says somewhere So this 2 times 10 to the minus 6, 10 to the minus 9th meters, that's the same as 2.6 nanometers. And the size of an atom is roughly 2 to 4 nanometers. And so now you've got the uncertainty of where that electron might be is over the whole volume element, if you will, of that atom. You have no idea where it is at any given time. And that's what Heisenberg was saying. That the you know more about the position, the less you know about the momentum. If you know the momentum, we know the mass of an electron and its velocity, you have to know its position all the much less. And so that's sounds like a lot of mumbo jumbo. Don't let the trees obscure your appreciation of the beauty of the forest of quantum mechanics. The bottom line is that the uncertainty for that position for an electron is just so great in regards to the size of the atom that it becomes important. Whereas in the macro world, where this Kia Forte is, that its size, its uncertainty in position, it becomes much less. Thanks for listening.